where we are talking about the tools of chemistry. Essentially what we're going to be, a lot of the things that you're going to be doing in the lab, and maybe show you a little bit of the techniques and see how much you remember from Gen Chem. And then we'll talk a little bit about significant figures. So what's the big deal? Well, there's a lot of big deals, but one of them is kind of obvious, like the forensic science laboratory. They're always after not if it's cocaine or not, they're after how much cocaine. So you screw up in those calculations or that analysis, with your technique, it's not good. And it's surprising that 63% of all the errors are essentially due to poor technique. So it's important. A few of the safety highlights. And it'd be nice if all these chemical manufacturers would stick to the same little label, but not all of them have this nice little multicolored label on there. But some of them do, so that's why we're talking about it. But before we do, contact lenses. Oh, that's a good question. Gloria, I don't know if you wear contact lenses or not. Let's say you do, right? And got a good deal on them, because glasses I'm supposed to, everything's blurry back there where you are, Gloria, but I know it's you. So I should probably be wearing glasses, but if I had the choice, I'd probably wear contacts. And the point is, why can't you wear contact lenses? They're so much more comfortable in the lab, right? Not so much absorb as stuck, trapped. The problem are these acids. You've heard of hydrochloric acid. You've heard of nitric acid. What's the other one? They're gases. But they look all syrupy. Well, yeah, they bubble them up through water, a lot of it. And that's that concentrated acid. Those are gaseous acids. So if you're working on them, even if you're using the fume hood and you get a waft of it, somehow those gases can permeate, through the contact lens. And then behind your eyeballs, all this nice wet stuff, water. So then it's not just a gas, it's hydrochloric acid now. And then, this kind of burns a little bit. So you come over to the little eye wash, as Smith says, to wash your eye out. It's not getting any better because it's under the contact lens. So that's never happened, but that's the story I read. So that's why I'm reporting it to you. So, and it makes sense. It's never happened to me, but maybe that's because one, don't allow it, but I can't tell, right? You can't have it memorized who wears glasses and who doesn't. But no one's ever really had that. But I wouldn't mess with it. I wouldn't wear. And plus, the glasses are, right there. You have extra eye protection there. Because the number one danger, according to Smith, isn't chemicals in the lab. It's what? What did I preach on? Glass, flying glassware, especially with Monica in the lab, right? So glass goes everywhere when you break it. So chemicals you can wash out. Glass, ugh, I can't even imagine that in your eyeball. Okay, anyway, so we have these safety labels. In a chemical hazards label, the numbers go from, what would you guess, Danielle? What to what? Lowest is 0. Well, Danielle's not even here. 3. Go from 0 to 3. So 0 would mean, don't worry about it. 3, you better worry about it. Well, what are the different things you can worry about? Blue, red, and yellow. Blue is for, anybody know this? Andy, what's the blue for? Health. The red, probably everybody is for? Biohazard. Well, that's flammable. Now, hang on to biohazard, Gloria. We're not there yet. How about the yellow? Not biohazard. There's some compounds where, I don't know, this has been on the shelf for eons, right? And it hasn't been jostled, moved, nothing. You don't live in California, it's not shaken, nothing like that. And then you go up to the shelf and you need it. You grab it, you shake it a little bit, it explodes. The problem is there's a lot of compounds, especially anything with a per in it, a lot of those, they form these gases. And all it does is just build up. And you should have it vent, but where would you have it vent to? If you have it vent, every single storage area has to be, properly made, but a lot of them aren't. So they don't vent these little guys. So it just builds up pressure more and more and more, and then it can explode on you, especially if you shake it a little bit. So what do we call it? Explosivity? Is that a word? I don't know. Something like that. Okay. You have biohazard. You have, I don't know, some little special thing where this stuff goes through your gloves. Like, what was that? Dimethyl mercury. Some lady I forget where she was. She's doing NMR and the stuff, wearing the gloves and everything, right? But she ends up dying because the stuff goes through the gloves. So any of those special, kind of like miscellaneous or, special, something that you should be aware of. Don't store this here because this is going to happen. It's just special rules, instructions, especially regarding your safety, though. Not really so much storage, but okay. Why would technique be important in a forensic science lab? We kind of already talked about it. Research lab, I mean, if you don't get the right answers, it's not going to be reproducible. Or you could really hurt somebody's life here. An analytical balance, one of the tools that you're going to use a lot. So what I want to do first is I want to mask some sodium chloride. So it's facing you guys. But I should be able to do this backwards, not that big a deal. Let's say this is in lab, you have to mass out some solid, some amount. Okay, so how do you do it? What's the best way to do it? Because pretty much all your labs in this course, the beginning ones not so much because we're learning how to do spreadsheets and making some solutions and stuff. But the majority of the labs, you're on your own. And yeah, there's folks around you doing the exact same thing, so you can talk to them and they can help you out and you can help them out. But each of you are responsible for your own unknown. So your reports, that's a good chunk of your grade. Did you get the right answer or not? It's all technique. So you want to have good technique using the analytical balance. So what I did first is I folded the paper because it'll be easier to pull out of there. So, and I don't want to take the mass of the paper into account, so I'll do the T word. What's that? Tear. Okay, and let it settle down. Notice how all the windows are nice and closed, and that's all good. Okay, now it's on 0. And then what I'll do is just open the glass side up part way, so then I can be hitting this, and it drops off those little bits. See what I'm saying? Uh-oh, somebody wants in. No, you can't come in, Danielle. You left. You can't come back. Oh, I thought you were Danielle.
Hi, Professor.
Hi. What's up?
I miss playing sand volleyball, but here, you got 2 letters for it too, so.
Oh. But Ariel likes to go by Sabina. Friday at 5. Okay. What was her name again, Ricky? What was her name? We played volleyball with her and all summer. Isn't that sad? All right. So the point was we were trying to get. God. Okay. So, you try not to make a mess. All right, I probably put too much on there. The spatulas with a little micro scoop are easier to use. I remember that, dude. All right. So you can kind of tap whatever you want. You're watching the numbers, and you kind of tap, and then you stop when you get what you want. Okay. And then you close it, and you write down all the numbers. So that would be your mass. 0.0630. Okay. So how do we calibrate these things in the first place? Okay. So we're going to, now let's leave it on there for now. To be honest with you, I'm not so worried about calibration The reason why is, let's say this is off by 1.2689 grams. Oh man, Smith, you just said all my labs are based on whether I get the right answer or not. But every single mass that you do is mass by difference. So you really don't care. You see what I'm saying? So you're massing by difference. So whether the calibration is off, all readings are too high or all readings are too low, you're massing by difference. You really don't care. But it's nice, like this. It's kind of gone away. I should be more careful with this. But how do you calibrate? These El Cheapo balances, you have to get an actual weight, and it says 100.000 grams on it. And then you push the calibration button, put it on there, and just let it calibrate itself. The nicer analytical balances, you'll hear them. When you go into the, because that's what you guys will be using, when you go in there, and we're doing in lab, sometimes you'll hear this, you're not even doing anything. It's calibrating itself, and it just does that on its own throughout the day. So that's kind of nice. Buoyancy. Okay, what is buoyancy? Let's say, I want to do this. I want to fill this up with, let's say, this is the general chemistry lab. I want to do a lab with ideal gas or something. Anyway, the point is I want to fill this up with oxygen. I've got a balloon filled with oxygen gas, or a bag. The balloon would pop, right? So it's a bag. So I puncture the bag, suck up the oxygen gas, right? Suck it up, and then maybe put something in here to keep it there, right? Seal it. So I have this nice container filled with oxygen gas. And it seems really convenient, right? Because I've got the volume, and I just want to know the mass of it for this activity in general chemistry. Okay. Well, here I could mass this guy, so I would put him on there. I don't want to lose this. We need that for later, I think. Whoop. Oh, let's make sure he's teared. Is he teared? Tear it. Okay. So I want to mass it full. Oh, I can't read that. Mass it full, it reads 80.1515 about. 80.1515. So that's with the syringe full. Okay. Now, I want to mass it empty. Right? So then I can subtract the two. Get it all out. I have to put this stuff back on there, otherwise I'm going to be off, right? I guess I got to put him in here, otherwise I'm going to be off by the mass of a nail. Okay. Can't quite close it. 80.1529. So little Gen Chem kids are kind of wondering what the hell's going on. Does this make sense? Here it's full of a gas. Here it's supposed to be empty. Does that make sense? Which one should be less? Empty should be less. So you subtract the two and you get the mass of the gas. Something was measured wrong. This was measured wrong. If I want to measure the mass of this, it needs to have the exact same density. What's density? Mass over volume, all right? Mass over volume is density. And what's strange is, and this is what's hard to get used to. What I mean is, what are we surrounded around? What did we sink in? We're all sunk. We're sunk in what? An ocean of air. Is this stuff thick? You don't think it is. how much weight right here, 1 square inch, how much weight is on that 1 square inch? I put it on this table. How much weight in that 1 square inch is there due to air? Seems like hardly anything, right? It's 15 pounds. It's atmospheric pressure. You are in the bottom of a very, very thick soup of air. 15 pounds per square inch. Your whole body's, it's 15 pounds per square inch everywhere. Right? That's thousands and thousands of pounds of pressure. I would be smashed to a piece of paper if I didn't have air inside me, right? Because I have atmospheric pressure both inside and out. So everything needs to sink to the bottom, or at least sink to the same, see what I mean, the same level. The sinking idea is what I'm trying to get across, because it's buoyancy. I sunk to the bottom, but I'm still somewhat buoyant. So if I want to get the mass of this thing, right, I want the buoyancy to be roughly the same. This shape versus, now I'm going to need help. You're going to have to put the nail in. All right. Or maybe I can do it, because if I just grab it this way. So this shape, this volume versus, oh, I got twisted around. Right there. 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 That volume versus this volume. Huge difference. There's a huge density difference between, because this is an empty syringe, right? Did you see it? I had to pull pretty hard. I didn't let any air in there. Let's make sure he's teared. He's teared. This is how you mass an empty syringe, because you want the density as close to the same, the buoyancy factor, because you can never get rid of this buoyancy air. So you want the density to be about the same all the time for everything you measure. 79.9, 79.9, what does it say? 906. Much more believable. It better be less. I think I had air in it. Make sense? So if buoyancy is just that. You want everything that you measure on the analytical balance to have the same buoyant properties. You don't want to measure something hot and then mass it again when it's cold. Different buoyant properties. You have convection processes going on there. This is just very exaggerated buoyancy issue. There's equations to take care of buoyancy. However, what I do is I don't take into account those buoyancy equations when I make up your unknowns in the lab, and therefore you don't take into account buoyancy when you mass your samples in the lab. So our buoyancy air just kind of, and everything's at room temp, so we're okay there. You kind of, since we're doing initial minus final, we're massing by difference. So that's kind of what buoyancy can really mess you up. Volumetric glassware. Here's one. All right. Desiree, that reads how many mils? 100 milliliters. Right? Where am I? Okay. We're not supposed to store which one? Kimberly? Acids, bases, or organics? Which one are we not supposed to store in glassware? A lot of little details in the reading, but I'm just plucking some out. You have a 33.3% chance here. Well, some you should be able to rule out, right? Like organics. What can organics, like methanol or whatever, what can that do to glass? Nail polish remover, all that stuff is stored in glass. No big deal. It's one of these two. Bases. Bases actually react with the glass and eat up the glass. So your base would be less strong than what you think it is. Okay. What is the tolerance of a 100 ml volumetric flask? Okay, someone who has really good eyes. Andy, what does that plus or minus number say?
0.16 milliliters.
0.16 milliliters. So for this one, It's plus or minus 0.16 milliliters. So what does that mean in the lab? I mean, you fill this thing up. What does it correspond with? Oh, I can dump it out and get 100 mils plus or minus 0.16 milliliters? What does it mean? It's the air, yeah, but in what volume? You can't take it out of here, right? You have to, first, I really don't even like this tolerance idea, because if someone's going to use this volumetric flask correctly, what do they have to do? How are they supposed to know when to stop adding solvent? The M word, the meniscus, right? Now you're talking about everyone's vision. Everyone's vision is totally different. And that bloody meniscus, right? Remember that? Where's my pen? Oh, yeah, I wanted to ask you about lab. Tomorrow, lab is supposed to start at 8, right? However, we're just going to talk about lab check-in procedures, make some solutions. I don't see that taking us 3 hours, 4 hours. So I'm willing to start at 9 if you guys are, right? But so let's take advantage of all we can, because once we start doing labs, then we gotta get here early. But so let's meet at 9 again tomorrow, okay? All right, so we were talking about the meniscus, right? And I lost my pen. Here it is. Okay. All right. That bloody meniscus, right? So you want that bottom of it to be right on the line. And it's all, you remember, if you ever look really close at meniscus, it's kind of glary and reflecty-like. So, I don't know, it's kind of hogwash, I think, this tolerance, because who can do that well? But what's important to realize is, can a 100 mil volumetric flask be used to deliver 100 mils? Right? Can I use this to deliver 100 mils with this tolerance? It's not built for it, right? It's not built for it. So you could use it to get roughly 100 mils, fill it up to the mark, right? But it's definitely not the Aliquot word. Maybe you've heard of that word, right? Take an Aliquot, 100 mil Aliquot, take 50 mil Aliquot, take 25 mil Aliquot. There's a lot of ways to get volumes, but when they use this word, they want exact. Right? And you can't deliver exact with this. You can't deliver exact with a graduated cylinder. What's a graduated cylinder up here? Yeah, here's your graduated cylinder. Right? So you can't use that. That's not an Aliquot. So, good question. We'll get to that. You're all excited and you're waiting for the answer. Yeah, the P word. Okay. We did this one. Okay, now we're here. Using the mass sodium chloride and the 100 ml flask, what will the concentration of sodium chloride equal? How would you prepare this aqueous solution? Okay. So, hopefully some didn't blow off. You would have done this right away. See, another point of folding the paper is because the balances are out in the hallway, right? And then you got to come across the hallway, come into the other lab, and then you got to find your workstation, and then you got to have everyone walk by and breathe and everything. So, right? So you want, that's why another reason for having it folded. Okay. So, how would I make this solution? I know that I forget the grams, it's written up on top. But first I'll get as much as I can, just flattening the paper out and holding it over. But odds are not everything fell in there. So what I'm going to do is use the little DI water container and get the rest of it. Especially some compounds that you're going to be masking, they're really powdery, and they're really going to stick to this wax paper. So it's important that you get all of it. So you just kind of, okay? And then once you got it all, he goes in the garbage, and then this guy just gets filled up to the mark. Bless you. All right, get it all to nice and dissolve really well, and then you'd fill it up to the mark. Oh, that was close. All right. If you go over it, you're just screwed, right? You got to start all over. If you go over the mark. What's parallax? Because I want to use that meniscus idea, right? And get it to stop right on the line. What's parallax? Got to be at eye level, so I only see one line going across. If I hold it down here, I see the circle. Hold up here, I see the circle. I need to see one line going across. And then just slowly drip it in there.
And then you pass through the deficit.
Right? Now that's PhD perfect. Should we pass this around? Monica says all right, so that's the idea. Make sense? Okay. Notice I shook it up before I filled it up to the mark. It's a lot easier. And oh, this has happened. I'm glad I thought of this. So people are really careful getting it to the mark and things. And this happened, I think it was last lab in analytical. Folks were doing their titration. And they made it up, they made up their solution, and then just completely, and I was watching. I thought, there's nothing you can screw up on here. I was watching everything you did. And what they did is they forgot to do this. You'd probably have a cork or something in there. How many times do you have to do this?
As much as you can tolerate.
12. 12 times. Somebody did some study to analyze what it actually takes. So once or twice may have been more what those people even did, right? Maybe because once you see it looks clear, you think you're done, right? You just want to go on to the next step, especially if you're just kind of working with other folks, doing what they're doing. But man, don't forget to flip it over. Invert it at least 12 times, and then you're good to go. So that's important. So that's how I would prepare it. How would I calculate the mass here? What? We had, where'd it go? Here it is. 0.063 grams of sodium chloride. Divide that by the molar mass of sodium chloride. Divide that by the volume in liters. What is the molar mass of sodium chloride? 23 and 35 is about 58. Right? So then I'd have the moles on top, divided by the volume, and I get my molar mass of sodium chloride. I sort my molarity of sodium chloride. Right? Sometimes it's called big M molar, right? Molar sodium chloride. Okay. Here's the aliquot. I was thinking about bringing someone up here to see if they remembered how to do this. Because isn't this the worst part in the general chemistry lab? Is using these, there must be some better way to do this, right? So what we want to do is you want to get, let's say you want to get a 50 mil aliquot. You have to go hunt down one of these that say 50 mils on it. This is called this is burette. This is called a pipette, right? So you find one. And then the idea is to fill it up exactly to that mark, and then you take it to wherever you want to go and let it dispense, okay? If you find one of these that work well, your life is going to be so much easier. So that's the key, I think. So first, get all the air out of it. Now, the trick to getting air in and out of this thing isn't to squeeze it, because then you're just going to make it worse. What you want to do is imagine there's a little ball in there, and you want to kind of go like this to dislodge it a little bit so the air can get through either one way or the other. So that's why I kind of squeeze it one high, one low, and kind of push it like this or something. Try to dislodge that BB. So I try to dislodge that BB, and then it comes out a lot easier. And you can oh no, you can't. Maybe Ricky can. I can't. All right, so we get all the air out, jam it on the end. Okay. Now there's a lot of different spots that you can squeeze, right? Now the one that makes the most sense will be this one, because it'll suck the liquid up. Hold it nice and vertical. And it's best if you don't touch the bottom too, because that's going to slow everything down. See how it stops? So lift it up. Okay. And then this usually happens, right? You got to pop it off. You're losing it. So you got to put your thumb on it. Then you got to yell, Desiree, can you get the air out of this for me? I want to use the P word, please. Okay. Then you put it back on there. And you do it again. Okay. Now here's what I was talking about if you got a good one. I got a good one, right? It's not moving. If it was moving on me, I'd have no choice. I'd have to pop it off and then use my thumb. But since it's not moving on me, I can use all the little buttons that it's meant to be used. So I can come over and here's an exit button. And it's going to, oh man, it goes fast, doesn't it? There, I got lucky. There it is. But this says he's really touchy. See how fast it goes? So I really just prefer doing it with my thumb. Because your thumb, you just have that, you can feel it. So bring it up to eye level so you'll avoid the parallax. And the thumb, you can really slow it down or speed it up. It's so much easier. And then you're all ready to go to take it to wherever you need to go to dispense your 50 mils. And then it all dispenses, and whatever's left inside this at the bottom, you just leave it in there, right? It's supposed to be there. That's how it's calibrated. Okay, so that's an aliquot. The barrette, that's what this guy is, right? So one thing that, again, a lot of people mess up with, you're going to probably have acid or something in here, so you want to fill it up. So instead of climbing up on top of the bench, right, just take it down. Make sure this is closed. And then you fill it up. What I see too is a lot of, what you could do. A lot of people trying to get exactly on that 0, because then you don't have to do any math, right? And it goes down, and then you stop, and then you read it. But it takes a while to get it on that 0. But here's an idea I just thought of, because that's one thing, but the other thing is you haven't filled this part up yet. So if you go through all this work of getting it on 0, you come over here and you start adding. Once you open this up, first you have to fill this up, and then the rest goes in here. So you're already off. So what I think is a great idea is go over. If you really like this 0 thing, go way over, right? Now, open it up into some waste container, right? Open up the valve nice and slow and get it right on that 0. There. Now everything's ready to go. This is good. That's good. It's on that 0 that you want so bad. And this is filled. So that might be a good way to fill those barrettes. Masting solid. What's meant by bringing a solid to constant mass? Some solids that we're going to have in the lab that I'm going to have you analyze, they form hydrates, and they grab water from the air, and right, bring something to constant mass is just heating it, and you're going to drive off all the water. So you heat it up in the oven for who knows how long, whatever you want to do. You take it out of the oven, let it cool down in a desiccator, so you don't, otherwise the water gets back on there. And then you put it on the balance, write it down, right? Put it back in the oven, heat it up some more, desiccator, let it cool down, oven, and once all the water's gone, it's gone. You'll have a constant mass. That's what bringing to constant mass is. Okay, man, analytical lab is going to be you got to do that for every single run. What we are going to do is we are going to disregard the hydrates in lab. So in other words, when I'm making brandies unknown, I'm using this solid from this container, and yeah, it's got water in it. It's hydrated. That's how I made her unknown. That's what she's also going to analyze to make her standards. So yeah, but our results are going to be off, but not, from the actual true value, but from my calculations, since I use, see what I'm saying? I use the hydrated compound, so she's actually measuring the hydrated compound, not calcium carbonate, for example. She's measuring the hydrated compound. I analyze the hydrated compound. Did she get the same result? So it cancels out. So that way you don't have to do this massing to constant mass. I used to have a microwave oven because it was awesome. And it was big, right over here. It got stolen. I mean, it was huge. How could someone walk out with a huge microwave oven? But we didn't. Then that's when I decided, well, we don't even need this. We can just, everyone analyzes hydrated compounds. Okay. Experimental error. We're getting there. General rule to determine the tolerance. So, in other words, I don't know, you're reading a graduated cylinder. You're reading a barrette, right? You're supposed to write plus or minus what? Pretty much just figure out what the smallest increment is and divide it by 2. So here it's 1/10 of a milliliter. So if you write down a measurement, 24.2 milliliters plus or minus 0.05 milliliters, right? Just divide the smallest division by 2, and that's usually uncertain. That's just the convention. Or if you just want to say, be really lazy and say 20 plus or minus a milliliter, then you're not guessing between the lines, right? A milliliter is a lot. So this plus or minus tolerance thing is very subjective. It's how well you want to read something. Again, the conventional way here is 1/10 of a centimeter, 0.1 centimeters, or 0.01 centimeters, or 0.05 centimeters would be your tolerance, because 0.1 is the smallest division. Here's another ruler, except now look at the divisions. They're 10 centimeters. So if the smallest division is 10 centimeters, half of that is 5 centimeters, so you could say plus or minus 5 centimeters. But odds are you can probably guess better than 5 centimeters, but that's the point. It's just a general way of writing tolerance. And it's not something so much to worry about in this class, I don't think, but it's more of a P-Chem thing. And we're almost done. Significant figures, scientific notation. Okay. If I want to write a number in scientific notation, all I got to do is move the decimal place until I get this number A. And that's a number between what and what? 1 and 10. Okay? That's the easiest. There's nothing to memorize about sig figs if you just know scientific notation. So let's do that. Let's write this in scientific notation. It would be, what would it be, Gloriana, what would it be in scientific notation? 1 point. Well, we got to keep going. We got to name all the digits. 1.00 times 10 to the, yeah, we did it 2 times. To the 2. So now these exponents can either be positive or negative. If you look at the number and it's big, it's got to be positive. If you look at the number and it's less than 1, it has to be negative. This whole significant figure thing, if you write in scientific notation, count all the digits, and that's your number of sig figs. 1, 2, 3, 4, 5, 6. Then there's no question. Otherwise, you need to memorize little things, right? Like down here, how many sig figs there are. The answer actually is 5. But if you don't see it, just write the answer in scientific notation. And a lot of these zeros disappear. These right here, they're just placeholders. So move it over 3 places. I moved it over. I'm going to move the decimal place over 3 places. 1, 2, 3. So what I'm left is 1.5020. That's 1, 2, 3, 4, 5 sig figs, right? Make sense? So how about, here's a trick question. This is already between 1 and 10. So technically, you just write the same thing, but times 10 to the 0, because anything to the 0 is 1. So 1, 2, 3, 4, 5, 6, 6. Okay, big test. You get this right, I'll let you go. How many sig figs in this one, in this measurement? 1. If you write scientific notation, it would be 1 times 10 to the negative. Yeah, you got the idea. All righty. So have a good day. Oh, and there's a message up there for Ariel.